Biomedical science is a huge field with very different sort of use cases. So trying to get these two things to match, so what we as a computing center can provide, and then on the other hand, what the biomedical community would need to drive their efforts forward. Okay, few words about CSC. First, just out of the history from 1990s. So something that took place was that Linus Torvalds put his legendary code release Freaks to one of our servers, then to be distributed over the internet. And as part of the service, there was a IRC chat channel, and one of the community maintainers suggested that, oh, Freaks it's not a good name, you should change it because people don't take you seriously. Why don't you use Linux? This sort of illustrates that we need to have, so 1990s is ages back, but still we need to have the right sort of infrastructure at the right time and place for real breakthroughs to happen. And I mean, from the service provider's point of view, like CSC, it's not always clear what sort of infrastructure should be there. I think that cloud interfaces to our resources is one such thing that we need to really work on, and I think it presents an opportunity for the biomedical sciences in the similar aspect as this. So a word about Elixir. So this is an European Strategy Forum research infrastructure which takes care of the sustainability of biological data collections. So these are public open data resources for companies, universities and officials to work on. They contain human genome, they contain structures of proteins that can be used for designing new drugs that interact with those proteins, all the way through modeling of entire biological systems. Biology is computing nowadays. You can see from the usage of these data resources that there are more than 3 million unique users in the last year. So there are hundreds of people working at EBI in Cambridge, working on the data integration. So for example, how do you form links of the genomic components of a disease, for example, to words, how the different proteins are formed and how that affects. And what we have in Finland is a special collection of biological samples called biobanks, which contain information that could be integrated as part of the public data resources. So from the ICT perspective, so you can imagine how much public investments goes into producing this biomedical data in the first place. So I just brought one example of how much it cost 2008 to create the protein structures for drug companies and everybody to use. So people spent 520 million euros to produce the protein structures. And without this resource being online, we would not be able to develop the drugs, for example, that affect HIV virus. So we would not be able to control it with the small molecule drugs. So we need to have these resources to have these huge health and economical impacts. How much goes into the ICT to take care of the data, to keep it online? So it's less than 1%. So you can argue that investing on ICT that protects this information and keeps it online for researchers and people to use, it's really good value for money. Now, okay, so biology is becoming more and more computing intensive science, and we can see this already that the data growth in the data collections, it exceeds the sort of capabilities of the information technology systems. You can see that, for example, in EBI Cambridge, the number of racks in the machine rooms, it doubles every 12 months. So even though the disk systems are more capable of storing more data in a smaller space, it's not enough. So what this means that actually the electricity bill will go up from millions to tens of millions during that time, because those racks, they consume the same amount of electricity for providers. Okay, so what do these communities then use compute infrastructures for? So computing systems like high performance computers and clusters, they have been built for physics use cases as drivers. I will illustrate two sort of use cases that help find out what sort of infrastructure design should be in place so that we could be able to service the biomedical communities better. So the first one of these is classification of all known proteins from human, birds, snails, you name it, into families, so that you could actually see the similarities between mice and men, for example. This is something that we did a few years back with the EMBL-EBI as part of an Elixir technical feasibility study. The point here was that this is a very good computational challenge, because in 2008 we could already see that if they would create a database that provides this information for the community, so if we would have full updating cycles of the workflow that creates a database, so it would be about 700 million CPU hours. So how do you deliver that sort of resource for the biomedical community? That was one of the things that we sorted out. Basically, we went there and worked with the biomedical researchers and drew the workflow that they needed to accomplish before they ended up with the final database. And what we were able to recognize that, okay, there are some parts in the workflow that are very computing intensive. So what we did as part of the feasibility testing was that, okay, we take this compute intensive part, take it from the biomedical service provider and export it to CSC, which is a specialized computing provider. So this is what we did as part of whether we could actually integrate into the service provider's service creation workflow. And one thing here is that Cambridge is 3,000 kilometers away from here. So how do we work with the network? So does the network perform in the way? I mean, if you would sort of think about that, the public data resource provider like EBI would work with a compute center in the Nordic side. So I mean, the predictability and performance of the network is very important. So we researched how the network worked, and even the public network is capable of delivering that sort of use case, but it's quite clear that we need some sort of optimization and surveys of the network if we work in a distributed manner to produce the data services, because this is the key for the biomedical community, so that researchers can use it. So I mean, back in 2007 and 2008, I think when I first went there at the EBI and told that I'm from a supercomputing center, people are kind of cautious about this. So because their experience on computing centers has been that the interfaces towards them has not been optimal. But quite quickly that sort of prejudice was vanished, since they sort of saw that we were able to adjust our ways of operation in the way that we could actually provide a service for them. And this, I think, is the key. So expert involvement in the use cases is from different organizations specializing on different aspects is the key. Back to Finland. So what we have going at the moment is that we have a collaboration between CSC, FIM, which is the Finnish Institute for Molecular Medicine, placed in Meilahti area, and then THL, so National Institute for Health and Welfare. So what we are trying to do now for Finland is to create us a profile in the biomedical research infrastructures. And for this reason, we have I have another use case I'd like to show. What sort of data we have at the moment is that we have something called Finnish Gene Atlas. So it means that about 40,000 Finns have had their genomes read through from the start to the end with quite tight com. So we sort of a map of 40,000 Finns who sort of represent the Finnish population in general. And what we can already see from this data, based on the computational principal component analysis, is that Finns are unique on the genetic map of Europe. And what the biological investigators would like to do is use this sort of population-based cohorts to understand the genetic, so very deep level components of major health challenges like high cholesterol, diabetes and heart diseases, which on the statistical level are unfortunately abundant on the Finnish population. So creating the link between the genetic components that make you vulnerable, for example, to have a diabetes. And what is special about Finland is that we have a unified approach as we try to work with the medical community, and then we have a specialized computing provider, CSC, to work here. But this is a sort of a long way towards the cloud interfaces, but I mean, it's very important that you understand what the end users of the cloud would like your platform or infrastructure that you provide as a service to achieve. So this is the sort of workflow that biomedical researchers, Samuel Ripatti's group, principally drew to us that what they want. So they have data resources, they have some computational resources, they have prediction methods. Altogether, these form a sort of a very complex software stack that we would have to run on our platform. So they have sort of software stacks in the range of tens to hundreds different software pieces developed by laboratories in Finland and abroad. And they want to combine these all into a software environment. And what we need to do is to somehow encapsulate this environment that the research groups want to create on top of the resource that CSC provides, clusters, for example. Security is one of the issues that we have not yet addressed properly. This is an added cost for compute provider, for example, if part of this data set is something that you definitely don't want to be in the public domain. And still again, you need to link the data resources that are in the public domain. So I mean, this creates real big challenges for the security. What we have done just recently, a few months back, is that we have a technical proof of concept how we can actually achieve this. So we have a cluster resource here at CSC, and then at FIM there's another cluster. What we are able to do through a private network solution is that we move the number of cluster nodes to the local cluster. So basically the local maintenance IT experts at the local institute at the moment, they have the option that, okay, we have a cluster locally, and we need to run it, we need to keep it up to date, we need to scale it up at some time. So we are already capable of providing them the option that instead of buying a physical machine and physical node to their cluster, we can provide for them one identical node through the private network solution. So this, to my view, is a cloud. This is a commercial break. So I mean, we need to be compatible with the e-infrastructures that are developed in Europe. So the other national public efforts to deliver these types of new interfaces to computing capacities. So Finnish National Grid Initiative (FGI) is very important. So we have a proof of concept. We have needs from the biomedical community. What is the next step? So this is the bleeding edge for me, at least. Next year we will try to productize this new type of interface to CSC resources for the biomedical science. So how we sort of evolve the service forward is that we have this one use case which already has been very successful on how the statistical linkage of the genomic components is done, and we will extend it into more use cases, more workflows, more software environments in the future during the next year. And what we really will do is we will work with the biomedical service providers so that their task becomes easier. We have a vision how we could integrate into the European activity. So basically, different organizations like Elixir and biomedical institutes, they are providing public biological information into the internet. And journals, science, nature, so forth. So they require people who publish articles to submit their data to public repositories. And how Elixir has already reacted is that they have built new data centers so that they can keep up to date with the supply of the information for the end user. We have things that affect, and legislation is one. So Finnish law for biobanking should be expected to be in force. Maybe not next year. This is maybe an optimistic date. It's an old slide. Maybe it's more close to 2012. We have national research data policies that will affect what sort of service we should provide.